When we use one of these numerical techniques like the trapezoid rule or Simpsons rule, we know that we're only approximating the integral. Although it would be nice to know how close are we expecting our approximation is going to be to the actual answer. Right? In both types of approximations here, we're subdividing the region into n pieces and then using either straight lines for the trapezoid rule or parabolas for the Simpsons rule to approximate those areas. Um, and the error is as follows. For the trapezoid rule, I'm going to call it E sub t, the error in our estimate is going to be less than or equal to, what is this now here? K times v minus a cubed over 12n squared. Now this formula comes from a little bit more advanced calculus than what we've done so far. At this stage, we're just going to give you that formula. If you take a sequences and series class or an advanced calculus class, you could quite possibly see where this comes from. It's not too difficult to do, but it's beyond what we want to do right now. K, I need to mention, where on this one, K is any upper bound for the second derivative on the interval. Any upper bound for f double prime of x, actually the absolute value, on the interval from a to b. So you look at the second derivative and say, how big does it get? Actually, that to me makes some good sense here in that if you think about the trapezoid rule, on each interval, you've got a function doing something like this, and you're approximating it by a straight line. Well, the error is going to be dependent on how much that thing bends. And the second derivative is one of the things that indicates bend, how the inflection, that's the second derivative thing. So it makes some sense to me that the error in the trapezoid approximation should be related to the second derivative. So that comes in here. The error also is related to the length of the interval, b minus a here. The longer the interval, the more you might expect error. And so that's actually related to the length of the interval cubed. The error is also related to n. That is, with n in the denominator here, the bigger n is, the smaller you'd expect the error to be. Right? Smaller values of n would give you potentially bigger errors. Okay? So this is the error formula for the trapezoid rule. Let me do one example of that, and then we'll do Simpson's rule. So let's do just an example here. Suppose I'm looking at the integral from 2 to 7 of, let's say, 1 over x to the 5th dx. Okay. And I'm going to use the trapezoid rule with, let's say, trap rule with n equals 4. Actually, let's do 5. I only say 5 because if I were actually doing this, delta x would be 7 minus 2 over 5. So delta x would be 1 in this case. That would be a nicer number to use than 4. But anyway, the error approximation here, I need to know, well, I know b and a because b is 7 and a is 2. I need to know n, but n is 5, and then I need to know k. So I got to figure out what the second derivative of this function is doing. So let's take a look here. I've got f of x is x to the negative 5. The derivative would be minus 5 x to the minus 6, and the second derivative is 30 x to the minus 7. Right? Now I need to know how big does the absolute value of this thing get? Is how far away from 0 does this thing do? But if I know anything about this function, x to the negative 7 power is a decaying curve like that. The 30 just scales it up. But the point is, for positive values of x, this is getting smaller as x gets bigger. So I'm going from 3 here to 7. Sorry, 2 to 7 actually. 2 to 7. It's going to be as big as possible. The second derivative is going to be big as possible at the endpoint here of 2. So I want k to equal 30 divided by 2 to the 7th power. Well, 30 divided by 2 to the 7th power is 30 divided by 2 to the 7th is 0.234375. That's exact. So the error now in the trapezoid rule is this k, 0.234375, times b minus a, 7 minus 2 cubed. Is that right? Where's that error formula? Yes, b minus a cubed. So let's put a cube right there. Over 12 times n squared. So that's 5 squared. And when I calculate that, it's equal to 0.0976, whatever, 56. So whatever I get when I use the trapezoid rule with n equals 5, I know that my answer, my estimate of the area, is no more than 0.09 away from the actual answer. So if I came up with an answer of 7, I know that the answer is somewhere between 6.9 and 7.1, right? That whatever it is, this is the amount of error at most that I might have. Okay? For Simpsons rule, the error of Simpsons rule is a similar formula here. K times b minus a to the 5th power over 180. Let's write that a little better. 180 n to the 4th. Okay. In this case, k is any upper bound on the absolute value of the 4th derivative of x, of f of x. Right? In the previous one, k was an upper bound on the 2nd derivative. For this case, it's on the 4th derivative. Now, one of the things I want to say, any upper bound, you actually want to get as small of an upper bound as possible. You're trying to find k to be bigger than, in this case, bigger than the 4th derivative. Since you're trying to get an estimate, you want that estimate to be as small as possible, and k is in the numerator here. So taking k as small as possible, but yet still bigger than the 4th derivative, then that's what you're trying to do. Okay, so let's do that same integral here. What did we do? 2 to 7 of x to the minus 5 dx. And I did n equals 5, but with Simpsons rule I can't do n equals 5 because it's got to be even. So let's cut it to n equals 4. So in some ways I might have less accuracy here because I've got a smaller value of n. But let's see if maybe that makes up for something here. I need b minus a. I've got that 7 and 2. N is 4. I still got to figure out k. So here we go. The function that we're dealing with here is x to the minus 5. So the first derivative is minus 5x to the minus 6. Second derivative is 30x to the minus 7. Third derivative is negative 210x to the negative 8. The fourth derivative is positive 1680x to the negative 9. Again, this x to the negative 9 is a decreasing function like that. So this fourth derivative is going to be biggest at the left-hand point here. So we're going from 2 to 7. The fourth derivative will be biggest at 2. So k is going to equal 1680 divided by 2 to the 9th. 1680 divided by 2 to the 9th. Holy mackerel, what is that equal to? It is 3.28125. Okay, so now I can calculate my estimated error by the error for Simpsons rule. It's going to be less than or equal to 3.28125 times 7 minus 2 to the 5th power divided by 180 and 4 to the 4th power equals, what does it equal? 0.2225 and some change. This is an interesting problem. Now granted, I used n equals 5 for trapezoids and n equals 4 for the Simpsons rule, but usually Simpsons rule is substantially better. This is an interesting example because this derivative, this coefficient out in front, keeps getting bigger and bigger and bigger each time. It's growing actually faster than that, because we're plugging in, well, I plugged in a 2 to the 9th power here to calculate k, where to do k for the trapezoid rule, I used the second derivative, and I had 30 times 2 to the 7th. Well, there's a factor of 4 here that the denominator grew by, from 2 to the 7th to 2 to the 9th. But there's, a factor of 7, there's a factor of 56 that this grew by. And so the numerator is growing faster. Quite often you'll find that it's the opposite, in that the denominator here is comparing the denominator of the trapezoid rule to the Simpsons rule. It's just a matter of this this denominator. I expect Simpsons rule to be better. In this example, it's not better. Okay. Now, two types of questions you're going to get. One is just like this. Here's an integral you're trying to approximate. This is the number of subintervals you're going to choose. What's your estimated error? You're going to approximate the value of the integral, but that's going to just be an approximation. So how much are you off by? Well, with Simpsons rule, this is the formula right here. Doing this integral with this value of n, this is the error that you might get. No bigger than that. Okay. So that's one type of question. The other type of question is, suppose I know how close I want to be to the actual value, then how much do I need, how many subintervals? Find n to get the estimate that close. Okay. So we will take a look at that type of problem in the next video.